In this lecture, we are going to discuss a popular machine learning technique called neural networks. The technique is known for its flexibility and the ability to model complex relationships that cannot be easily modeled by other techniques. Therefore, it has a wide range of applications in the modern world, ranging from financial market trading to autonomous vehicles. Neural networks is a data-driven approach for both classification and prediction. So as we discussed in other data-driven techniques, it tends to do a good job predicting future cases, but does not offer much insights about how the decisions were made. And at the same time, the technique tends to require large data sets to develop more accurate predictive models, as other data-driven techniques do. That is why, in today's large data environment, neural networks is becoming a widely used analytics technique. Neural networks is an important branch of machine learning, which mimics the function of the human brain to learn relationships and patterns in the data. In fact, as its name suggests, the technique is based on a model of biological activity in the brain, where neurons are interconnected and communicate with each other to facilitate learning and decision-making. In the biological process, it is believed that electric current flows between neurons, and that results in memories and decision-making capabilities. The process is simulated by computers in the late 20th century that became what is known today as the artificial neural networks, or simply neural nets. The technique mimics how humans learn or make decisions. As our experience tells us, a lot of time, how we make decisions is based on our intuition or gut feeling. It may feel like that these decisions cannot be rationalized, but they are actually based on our experience that is tapped unconsciously. This is quite similar to neural networks, as the rationale behind the decisions is often subtle and hard to explain. Therefore, we often feel that neural networks offer a somewhat black box solution to our problems and do not offer much interpretability as other model-driven techniques that we discussed before. However, such limitation is compensated by its high predictive accuracy and ability to support complex and subtle relationships. Applications of neural networks are widespread today. The most widely discussed of its applications would be the autonomous vehicles, which mimic human decision-making when driving to make split-second decisions based on a wide range of signs, road conditions, and mechanical readings. However, neural networks applications go much more beyond autonomous vehicles. The technique is widely used in the financial industry to analyze large quantities of financial data and in human resources to match talents with ideal positions. As the computer technology improves, the neural network applications will continue to diffuse into more and more areas of business analytics and our daily lives. Therefore, understanding this important technique will add a highly useful technique to your analytics toolbox. Now, let's go over some of the basic concepts related to neural networks. The basic idea of neural networks can be summarized in this statement. The technique combines the predictive information in a very flexible way that captures complicated relationships among these variables and between them and the outcome variable or variables. As with any supervised analytics techniques discussed so far, neural networks require both predict variables and outcome variables to model the relationships. It not only focuses on the relationship between the predictors and outcomes, but the relationships between the predictors at the same time. In addition, unlike many other techniques, neural networks may have multiple outcome variables. Although, as you can see in our demonstration later, the multiple outcome variables are actually multiple classes in a classification problem. As you will see from this slide, I have underlined the term flexible in the statement in order to emphasize this important characteristic of neural networks. In neural networks, the user is not required to specify the form of the relationships. Instead, the technique will apply various mathematical models that best fit the data. This is unlike regression techniques, where the user must specify whether the form of the relationship is linear or quadratic. This provides a very flexible way to model complex relationships between the predictors and the target variables. Although neural networks is not a model-driven technique, there are intermediate models that are generated in order to go from the predict variables to the target variables, as you will see in our demonstration later. The coefficients of these intermediate models will dictate the nature of the relationships, and they are continually tweaked by the new cases that are fed into the neural networks to improve the model's specification of the relationships. In other words, the network's interim performance in classification and prediction informs successive tweaks made to the model. Therefore, neural networks use an iterative process to incrementally improve its predictive performance. Each iteration can be a new training case or a batch of training cases, depending on how computationally intensive you want the technique to get, or the software tool that you use. The tweaking of the coefficients is again completely data-driven and done automatically by the software algorithm, which offers us little insights about the rationale behind the tweaks. Therefore, one key disadvantage of neural networks is its tendency to overfit the data, which means that the model fits the training data extremely well but fails to generalize to previously unseen datasets. Now let's talk about the architecture of neural networks. It is important to know the terminology associated with the architecture so that we can discuss it clearly. The diagram in this slide shows a what is called multi-layer feed-forward network. It is multi-layer because you can see multiple layers of neurons, which are called nodes. Shown as circles in the diagram, it is feed-forward because all the arrows in the diagram are pointing forward or to the right side of the diagram. So the nodes in the previous layer are feeding information to the nodes in the next layer forward. For example, there are 4 nodes in the first layer at the beginning of this network, and each feeds forward to the 3 nodes in the next layer, creating a total of 12 forward arrows. The first layer in the network is called the input layer. The input layer contains the predictor values, and each node represents a predictor variable. In this example, we start with 4 predictor variables. The last layer of nodes in the network is called the output layer, whose nodes represent the target variable or values. In this case, we have only one output layer node. It is common to have multiple output layer nodes in classification problems. In classification problems, each output layer node represents one possible class or category. For example, if there are m categories in the target variable, there will be m or m-1 output layer nodes, depending on the software package you use for neural networks. The reason why some software packages would only have m-1 output layer nodes is because if you know the probabilities of the case belonging to m-1 classes, then you would automatically know the probability of the case belonging to the other class, because the probabilities would add up to 1. All the layers of nodes between the input and output layers are called hidden layers, which produce the intermediate models that connect the input layer nodes to output layer nodes. The most popular type of neural networks is the multi-layer feed-forward network that is shown in the diagram here, and only has one-way flow and no cycles. While technically, you can have as many hidden layers as you want, and as many nodes as you want in the hidden layers. In practice, the neural network with only one hidden layer is the most popular kind and tends to perform very well. In addition, the more hidden layers and nodes to have in your network, the more computationally expensive it is to process the neural network. Now that you understand the general architecture and the terminology of neural networks, let's look at a more practical example to help you better understand how the technique works. This example illustrates how a neural network generates output from the predictor variables, and the concepts involved here can be generalized to more complex problems. Let's consider this very small data set with only 6 observations about consumer preference for various processed cheese. The 2 predictors or input variables in the data set are the relative presence of fat and salt in the cheese. As you can see from the data, we have already normalized these 2 variables so that both of them are on the same scale ranging from 0 to 1, with 0 being the minimum amount possible in the manufacturing process of the cheese, and 1 being the maximum amount. The target variable is acceptance, which indicates whether the consumers liked or disliked the cheese. As you can see, this is a binary class classification problem where the target variable is categorical with 2 distinct classes, like and dislike. Let's use like as the target class or class 1, and dislike as class 0 in this case. How can we transform this problem into a neural network? Well, as we discussed, the input layer of a neural network contains the predictor variables and their values. In this case, we have 2 predictor variables, fat and salt content. Therefore, we have 2 input layer nodes in our network, as shown in this diagram here. The output layer contains the target variable or values. Since this is a binary class classification problem, our target variable accept has two classes, like and dislike. Therefore, there are two nodes in the output layer representing the two possible classes. In some software products, you can have only one node in the output layer if there are two classes, as we discussed before, because the probabilities of the case belonging to the two classes should add up to 1. In this example, we are going to show the version with two nodes. All the nodes are numbered from left to right, with the input nodes having smaller numbers and output nodes with larger numbers, so that we can refer to them easily. Now the hidden layer is what shows the relationships between the predictors and the target variables. In this example, we have the simple but also the most popular one hidden layer structure with 3 nodes. Remember, the more nodes you have in the hidden layer, the network may become more flexible to model complex relationships. But at the same time, it also becomes more computationally expensive and increases the chance of model overfitting. So it is recommended that you start with a relatively simple network architecture and then increase its complexity incrementally to find the optimal fit. In our simple example, we will start with only 3 nodes, nodes 3, 4, and 5. We have added some more notations to our network diagram here, and they are the lowercase w for weights, and the Greek letter theta for what's called node bias. The weights and the biases are denoted using numbers that show their associated nodes. For example, W13 refers to the weight placed on the value in node 1 to compute the value in node 3. And W23 refers to the weight placed on the value in node 2 to compute the value in node 3, and so on. You can think of these weights as the coefficients in the regression model we have seen before. They represent the amount of change in the target node caused by 1 unit change in the previous node. The thetas, or the node bias values, are equivalent to the constant in the regression model. Theta 3 refers to the bias for node 3, and theta 4 is the bias for node 4. A mathematical formula is used to generate the values for nodes in the latter layers based on the values of the nodes of the prior layer, weights, and the node biases. Part of the mathematical formula would produce the weighted sum of the input values through something that looks just like the regression function that we are all familiar with, which is y equals to constant plus beta 1 x1 plus beta 2 x2 and so on. Except in the case of neural networks, the constant is replaced by the node bias theta, and the betas or coefficients are replaced by the weights. For example, to compute the weighted sum for node 3, we will use the following formula. Value for node 3 equals to theta 3 plus weight 1, 3 times the value of node 1 plus weight 2, 3 times the value of node 2. And to compute the value of node 4, we would do theta 4 plus weight 1, 4 times the value of node 1 plus weight 2, 4 times the value of node 2. Now pause the video and try to come up with the mathematical formulas for computing the weighted sums for nodes 5, 6, and 7 yourself. Please keep in mind that the weighted sums may or may not be the final values for the nodes. In most cases, some forms of transformation will be applied to the weighted sums in order to derive the final values for the nodes, and we will illustrate that later in our example.